So here we go with Chapter 10, Lesson 5. We're still in the chapter on similar triangles. Today we're going to be looking at, again, at proportions and then the dilation transformation. We'll be spending time on GSP in class on this very thing. To introduce this idea, the author brings in an old-time pinhole camera. Maybe you recognized it as such. There's a small hole here, and they put the film on the back wall. They'd cover the whole thing with a piece of black material, and then they would just open this up a little bit, long enough for the light from the object to go through the pinhole and form on the back wall. Now you may have noticed that here they're taking a picture of the moon, and it's on the top of the circle, but here you see it's on the bottom. It's because light travels in a straight path, so from the top here as it goes through that hole, it ends up on the bottom, and vice versa in the other direction. But geometry and similar triangles help us understand this a little bit better. So here we have a diagram. This would be the thing you're looking at, the object, and this would be its image after it passed through the pinhole represented by P. Let's do a little review first. See if you can figure out for yourself how you could say that triangle APB was similar to triangle DPC. So this triangle and this triangle. Pause the video, think about that a minute. There's really only one way we know triangles are similar at this point. Hopefully you came up with the idea of angle-angle similarity from our last class. You did have to assume that these two lines were parallel. So how do we get two angles equal? Well, you can do it a couple ways. One, if these lines are parallel and you think of AC as the transversal, the angle here, angle A, would be equal to angle C because they are what kind of angles? Alternate interior angles. You also have the angle at B equal to the angle here at D, so you do have two angles of one triangle equal to two angles of another triangle. Did some of you right away see that these vertical angles are also equal? So you have all three angles of one equal to three angles of another, but you really only need two for angle-angle similarity. So we've proven that the triangles are similar. Here's the question we're going to be addressing in this lesson today. What do you think might be true about altitudes EP and FP of similar triangles? I bet you have a guess for that. Well, let's take a look. So we're wondering what's true about EP and FP. Well, we're going to start first of all. Oh, I'm sorry. Got to back up one step. If these triangles are similar, we have several ratios that have to be true. The long side of this triangle put into a ratio with the long side of this triangle. That ratio would have to be equal to the shorter side of the large one to the shorter side of the right-hand triangle. And then do you have the third ratio? Sure, it would be this other side, this vertical side of the larger one compared to the vertical side of the smaller one. Each of those would make a ratio, and the ratio would be the same. And was your guess that the ratio of the altitudes would also be the same? If that was your guess, you're right. Let's see how that works out. Keeping in mind AB is the image, AB is the object, and CD is the image. First of all, we're going to prove that triangles ABP and CDP are similar. We did that, I guess. Let's take a look at these two triangles first. Let's kind of break this up. Can you prove that these two triangles are similar? Hopefully right away you saw that you can use pretty much the same process as we did for the entire triangle. We could use these vertical angles here, and then again, since these sides are parallel, we've got the alternate interior angles at A and C. So yes, they're similar. And because they are, we can write a couple of ratios. We're going to say that the hypotenuse, yep, it's a hypotenuse because this is a right angle here. The hypotenuse of this triangle in a ratio with the hypotenuse of that triangle is equal to the ratio of the long leg of the larger triangle to the long leg of the shorter triangle. So everybody can agree that that proportion must be true. We're going to use that same trick on these two smaller triangles. Can you see right away similarity? We've got vertical angles, and again we have the right angles here. Or you could use the alternate interior angles at B and D. Either way, we have similarity of those two smaller triangles. And guess which proportion we're going to write? Yep, we're going to go with the long leg of the left-hand triangle to the long leg of the right-hand triangle and set it equal to the hypotenuse of this larger triangle compared to the hypotenuse of the other triangle. So there's the proportion that we can write. EP to FP as BP to PD because the triangles are similar. Anybody guess where we're going to go looking at these two proportions? If you saw that we've got this ratio in both, we can substitute into that equality. And we end up with the fact that PE to PF is the same ratio as AB to CD. And yeah, there they are. The altitudes are in the same ratio as at least one of the sides here. But we know since those triangles are similar, all the other ratios were also true. So when we asked that question earlier, what do you think might be true about the altitudes of similar triangles? They're in the same ratio as the corresponding sides. So here's that in words, Theorem 46. Corresponding altitudes of similar triangles have the same ratio as that of the corresponding sides. You can spend a little time if you want, pause and look through this. This puts in words what we just did with our images earlier. So I'm going to pause a little bit longer on this theorem. Again, once again, corresponding altitudes of similar triangles have the same ratio as that of the corresponding sides. So here you see two triangles. They're similar, we're given that, and we've got their altitudes. We're trying to prove that those altitudes have the same ratio as, in this case, the bottoms, AC to DF. We already proved you could do that, but there are some other proportions you could write as well. For instance, these two altitudes, BG to EH, if we put them in a ratio, they should also be equal to what other ratios? Think about that a minute. Okay, I'm going to pick the left sides of the triangle. So the altitude of the small one to the altitude of the larger one has to have the same ratio as the left side of this smaller triangle to the left side of this one. Can you get at least two others here maybe? Okay, I'm going to get this one. And you're right, that doesn't have anything to do with the altitudes. But it's still true that BA is to ED, corresponding sides, as where'd I go? Yep, AC is to DF, the bottoms of those two. Similar triangles have proportional sides. I'm going to go back to the altitudes for my last one. Figure out which one's left. We've got this one with the altitudes. We have this one with the altitudes. Okay, here's the last one. Looks like we're just showing how we substituted. That's what it was. BG over EH is BA over ED, but BA over ED is AC over DF, so we can substitute. So this is another way to prove that theorem. We're going to be spending some time on GSP in class on Friday, our next class period. We're going to be looking at dilation transformations. If you recall, that's the center of the dilation. And if I were to tell you that the magnitude of this dilation is 2, what would that mean to you? Well, we have our original here, and this is our image. A magnitude with a dilation of 2 would mean everything on the image is twice as large as the original. That's what that magnitude means. Well, if that's true of the sides, then we find out it's also going to be true of the altitudes. So if this were 2, EH would be 4. If AC was 7, DF would be 14. If AB was 6, ED would be 12. So the altitudes have the same ratio as the corresponding sides. Chapter 10, Lesson 5. The first 18 problems, I think, deal with a fish story. Have you ever seen something like this where you hold a fish up and it's just as big as the man? So that's a big fish, huh? Well, not exactly. Here's a diagram showing what's going on. Here's the camera. And the fish is right up here at DE, and the man is back here at AB. Makes the fish look a lot larger. So we asked some questions about the diagram. You have to identify certain parts. Which line segments represent the distances of the fish and the man from the camera? So there's the fish, there's the man. Which one are distances? Well, it wouldn't be CD because that's not perpendicular. So CG is the distance from the camera to the fish, and CF, the camera to the man. And since they are that, they're also altitudes of these triangles, CDE and CAB. So CF and CG are altitudes. Question here, flashback. Well, since these are both perpendicular, what can you tell about DE and AB? Now they will have a question for you about CDE, the triangle, and CAB. Probably your guess is that they're similar. They're certainly not congruent. Similar, but you need to explain why you think they are similar. So think about that a minute, but keep in mind this fact that DE was parallel to AB, and use that same approach we used in proving our theorem today. A few more questions about the parts. We already answered that one. A little bit more. Now we're going to make a proportion. Remember the previous item had you talk about triangles that were similar, and if they are, then their corresponding parts are in the same ratio. So here we've got parts of the smaller triangle. We have the altitude compared to the base, or the right side of that triangle. So you just have to put the corresponding parts into this proportion. And name the theorem. Now you're going to plug in some values. 6 feet and 12 feet. The man is 6 feet tall, and he's 12 feet from the camera. What other distance would you need to know to be able to figure out the length of the fish? We need DE. You'd need something else. You'd need corresponding parts. Since we have the right side and the altitude, we would want the same two parts of this smaller triangle CDE. So make yourself a proportion here. Plug in those numbers. Plug in the 2 and figure out how big that fish is. So there's your proportion. Plug them in. So now here we've got 2 fish in a dilation transformation. Point E, remember what that's called. Measure the distances right in your book. Measure them out in centimeters. So I want you to measure BE and DE. If AB is the image of CD, CD is the original, and R1 is the magnitude, then BE, this fish, is the magnitude of, it's something times DE. I'm sorry, BE is something times DE. That something is R1, and that's the magnitude. So you could figure that out using your measurements on 10 and 11. What does this number indicate about the lengths of the two fish? So this magnitude number here, that should tell you something about these two fish. Now you're going to measure AB and CD and find the ratio of those two. Compare them. Going on yet with this same fish thing. If CD is the image of AB, we're going to do the same thing now. We're just getting a smaller magnitude. The image is going to be smaller than the original. So R2 is going to be a smaller number. And they ask you, what does that mean about how the fish are related compared to each other? They're not cousins. Use your measurements of AB and CD to find that ratio. And then take this R2 that you found. How is it related to R1 from the previous problem? Okay, we've got some givens here. I'm going to grab my pen this time and mark them in there. So AB up here, I guess that's marked, is parallel to ED down here in the bottom. And AD is perpendicular in here, so we've got 4 right angles. Perpendicular lines form 4 right angles. And we've got parallelograms. Well, that's helpful. The yellow ones are parallelograms. Each of these statements is either reasonable or not, but you have to have a reason for it. So they're asking, do these two triangles look congruent? And you give a reason. Do they look similar? And give a reason. Recalling that the only way we know how to make triangles similar right now is to prove the angle-angle theorem. Can you find two angles in this top triangle equal to two angles in the bottom triangle? Well, they got 2 of them made for you already. Give your explanation. Now, since they put this out there, they're wondering, is it true that AG to DG would be the same ratio as if you set BG in a ratio with GE? Well, that would be true if what were true? So look at 20 and then answer 21 and give an explanation. How about the areas of AGEF? This is the trickiest one. And BCDG. They don't look the same. But I'd ask you to take a look at number 21 and think about the means extremes property. And then answer this and decide. Area of triangle AGB and the area of DGE. Well, the area is how much space it covers up here. Does it look like those areas are equal? One last question about areas now of, this, be a little more careful here though, ADEF. So this trapezoid compared with this trapezoid. Are those areas the same? Keep in mind your answer to 22. This next, I believe, was sticky credit. If not, you have to work it through anyway yourself. This is a good problem. Washington Monument. It's got a rather distinctive shape here, but you know, originally it was going to not be like that. They ran out of time and they ran out of money, so they shortened her up right there. Tallest structure in Washington, D.C. I didn't know that before I saw this. So here we have a not-to-scale drawing of the Washington Monument and how it would have looked had they not run out of time and money. So first of all, how tall is the Washington Monument? Well, they've got some numbers in here. That shouldn't be too hard. The dotted lines show what the sides would have looked like and the altitude, FG, what that would have looked like if they hadn't changed things around. Now when they ask you to find a pair of similar triangles, again, we know triangles are similar if you can get 2 angles in one equal to 2 angles in another. So now you need to take a look at these. We've got a triangle there, we have a big triangle there, a big triangle there, and we have an even larger triangle here, FEC and FAB. So look at those several pairs of triangles and see if you can tell any pairs that are similar. Looking for two angles. Now they're going to put in a variable fg. So from the top all the way down to the bottom here, that's going to be the value of x. It's right inside here too, but I didn't want to scribble in there. If fg is x, write and solve a proportion to find out how tall the Washington Monument would be if its sides did not change. So we've got something equal to something. It's going to depend on which triangles you found here on 32. And then you would set their corresponding parts in relation or in ratio here. So if I thought it was triangle FEH and FAG, then I would set this part to this part, and then this part to this part. That might be one way to do it. If I thought it was triangle FEC, this top one, compared to the whole triangle, then I would find corresponding parts and set them in my ratio again. So that's what you need to do. Look for similar triangles and get their corresponding parts. Make a ratio. Solve it for x. And then this kind of a hint. State the theorem that you used. Well, this lesson is the theorem that tells you that the altitudes of similar triangles are equal, or on the same ratio, sorry. So maybe that's a hint as to the triangles that you might think about using. Here the author would just like to be sure that you know the difference between similar and congruent. So he asks you questions like, if you saw these two triangles, could you say they're congruent? If so, how would you know that? How would you know they're similar? Same question there. Here a little different question. Suppose that in these triangles, A over B was C over D. Would you know they were congruent if these ratios were 1? In order for this ratio to be 1, what has to be true about A and B? Same thing over here, C and D. If this ratio was equal to 1, what would have to be true about those numbers? Now, substitute those into your drawing here. Put them right in there. Substitute that thought into there, and then ask yourself, are those triangles congruent? And if so, why? So we're looking for side, 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 angle, side, angle, HL, one of those. Several times now in class I've told you that there are other ways to prove triangles similar. And some of you have stumbled across these already and said, hey, this seems to make sense. Well, here they are. One of them is side angle side similarity. In his previous book, the author developed these in the lesson. There were 2 extra lessons on them. Here he just puts them into a form of a proof, and this is a sticky credit item. Walks you through. It uses something similar to what we had done previously with side splitter. So you can work through these and give reasons for each of them for sticky credit. Hey, another problem. Suppose that for the triangles above, A over B is C over D is E over F. Those proportions are true. Would you know that they're congruent if those ratios were equal to 1? So again, you substitute this idea into those pictures and then ask yourself and give a reason why or why not. So here's our other sticky credit. It's side, side, side similarity. It's just saying if you can show that these two sides ratio compared to the ratio of these two sides compared to the ratio of those two sides are all the same, then you can say the triangles are similar without knowing anything about the angles. So that's a sticky credit item that you can give reasons for each of these steps. And the set 3 we can't do. They're talking about lighting a candle in a dark room and That would be against school rules. So again, the assignment is in Gradebook Wizard. I do hope that you've watched this. And I was thinking about at the very end, telling you, if you watch this, come up quietly to class tomorrow and tell me, and I'll give you a sticky credit worth 5 points. Don't share this with anybody. All right then, we'll see you in class.